Hi, this project is basically related to passive alignment flip chip assembly using the source surface tension of liquid solder and micromechanical stops. So in this complete paper, in the complete article, we have just used the laser diodes to post the bond alignment accuracy, which is basically less than 1 micrometer, and the implementation of the passive alignment in optoelectronics packing is still a challenge. Okay, still a challenge basically. So we are just going to improve its cost, high precision alignment in the flip flops, in flip chips basically, self alignment mechanism, as well as the micromechanical stops. So basically this paper presents the concept of passive alignment pursued, the experimental setup with the results thereof. It's the test vehicles is described, including the bump design as well as the bumping and the flip-flop flip chip assembly process. This passive alignment flip chip assembly using surface tension of liquid solder and micromechanical stops focuses on the developing of high precision and low cost passive alignment method for the assembling single mode laser diodes. Okay, so into the planar light wave PLC circuits, basically we call it PLC circuits. So the thing is that in the traditional, like for example, we when we just discussed that traditional logic active alignment methods, which is basically in optoelectronic packaging, which are very expensive and time consuming, demanding the sub-micron accuracy as well. So we have just adjusted it's that time consuming method with the yes, time consuming method with the micromechanical stops basically. And just a second. Yes. Okay. So in the testing of feasibility this method, we have just used the solder bumps through forming of electroplating, through sub fabrication of silicon substrates, through reactive ion etching to evaluate the feasibility of this method basically. Okay, so in the I have just written the complete abstract with the introduction. In the introduction I have just explained like how we have defined the planar light wave circuits through bond alignment accuracy within the submicron range. And the active, I have also discussed how conventional active alignment techniques, which are very highly accurate, but they are very expensive, high equipment cost. So that's why we need to reduce the cost through physical and chemical properties of materials. And how I also explained like how we can add the flip chip self alignment mechanism through surface tension forces generated through solder during the solder reflow naturally. And the next part is basically I have just also added the its fabrication, its testing, its the complete designing methodology of the reactive ion etching method for different cavities like mechanical stops and other surface tension driven alignment and mechanical constraints basically. So next one is basically I have written the passive alignment approach, like how we can add the passive alignment in this optoelectronics packaging viable. I have written the complete like I have already explained. I have used alignment accuracy better than 2 micrometer, which has been achieved, but our main target is 1 micrometer. And next one is I have added the compatible accuracy, and I have added the single mode compatible accuracy with the laser diodes on planar light guided circuit basically. And then the micromechanical stop circuits used in this case. Design and fabrication is that I have just written that how silicon test vehicles were fabricated using the reactive ion etching, and they were designed such as two corresponding dies with cavities and stops can be placed on each other. And we just need to add the scare bumps pairs of 300 micrometers width and 600 micrometer pitch were plated. And yes, this one is basically this photo provides us this figure one provide us the photograph of silicon test substrate with the nickel and AU pads basically. AU is a material of chemical properties of different material. So these are basically the stop points, and these are the pads. Okay, use nickel and AU pads basically. And next one, this figure presents a SEM of silicon test die. Basically, this is a die which die we called it its mechanical frame in which this chip is developed, and stops were etched using reactive ion etching, and AUSN bumps on the die were reflowed after the electroplating. Basically, this is we called it a frame plate, mechanical plate, in which we need to develop the complete chip system of the silicon. Okay. So next one, I have just added the substrate preparation and the chip preparation basically, which provide us the core section images of bump up to reflow, as well as it provide us the core section image after the consist of AU layer and um, eutectic solder cap and top, and on a top, and a layer consisting of intermetallic phase in between. Okay, so next one is basically I have just added that it's chip assembly, like flip chip assembly, how chip assembly developed in case of different superposition view from bonder chip, as well as the infrared microscope scope image of the alignment of silicon substrate. And next one is the infrared microscope image of the after the soldering process. And next one is a detailed picture of this complete. Okay, basically in the complete figure, it provide us the sample in different reflow soldering processes, and with the modification of chips, like how IR microscopy chip is developed and how it is inefficient and efficient for the different alignment of accuracy, as well as a chips movement. Next one is basically the left cross sectional view of flip chip assembly, and the cross section, as well as the flip chip solder joints as well. Okay. Yes, this complete structure developed for the images as well as the cross section flip chips assembly designs, and its complete picture of nickel pads. Okay, so next one, I have just added the conclusion. In the conclusion, basically I have just added like what accuracy I have achieved in the passive alignment flip chip assembly, and how we can produce its mechanical structure, how we can produce its test design through laser diode packaging, um, photonic integrated circuits, as well as optical interconnect systems. Okay, so this is basically, this chip is the more reliable and cost efficient circuit chip which is used in different vehicles. Okay, And next one is I have added the complete references. Okay. So if you need to ask anything, you just call me and I will answer your questions. Okay. Thank you.